Hello everyone, my name is Shengwen Liang. I am a student from Institute of Computing Technology, Chinese Academy of Sciences. Today, I will introduce EnGN, a high-throughput energy-efficient accelerator for large graph neural networks. This talk contains 6 parts. First, I will introduce the background. Recently, graph neural networks are becoming a progress field with diverse applications such as recommendation system, traffic forecasting, point cloud, and chemistry. Meanwhile, we also witness some organizations leverage graph neural network to repurpose drugs for fighting COVID-19. Why graph neural network can achieve such improvement? We give an example graph convolution network to show its computing pattern. Node classification is a typical GNN workload. For example, given a social network that each vertex represents a user and each edge represents the relation between users. This social network contains 2 groups. In this case, how to determine the user belongs to group 1 or group 2. In this figure, each vertex contains a feature vector, which contains the information of users. First, GNN condenses the feature of each vertex in the graph using a neural network. After that, GNN embeds the graph topology into local vertex feature by accumulating each vertex label feature. Finally, GNN leverages a nonlinear function to each vertex for determining the label of each vertex. Graph neural networks have performed their powerful performance in different fields. However, the characteristics of CPU and GPU make both unable to support graph neural networks efficiently. Therefore, before customizing hardware accelerator for graph neural networks, we need to build a computational model for graph neural networks. To this end, we first investigate different graph neural network models and select 4 typical models: GNN, graph CGPO, gated GNN, and GNN. First, for the GNN model, the feature vectors of the source vertices will first perform a tensor operation, and then perform the graph aggregation to the destination vertex. And for graph CG model, the destination vertex also needs a tensor operation. Unlike the first 2 models, the source and the destination vertices on gated GNN model need to perform tensor operation together. For the GNN model, the destination vertex is used to perform a GRU operation. GNN algorithms are different in terms of architecture and target applications. We notice that they share common computing patterns. Thereby, in order to cover most GNN models, we build a unified graph neural network processing framework, which includes 3 main stages: feature extraction, aggregate, and update. The feature extraction stage condenses the property of each vertex in the graph using a neural network. The aggregate stage embeds the graph topology into local vertex property by accumulating each vertex label properties generated in the feature extraction stage. The update stage leverages wet parameters to condense the output features in the aggregate stage, then applied a nonlinear function to each vertex of the graph before output. By using graph neural network processing model, we can map different GNN models to the processing model, which will bring great convenience to our hardware design. To gain insight into the computing pattern of GNN models, we analyze 4 typical GNN models which cover the major areas of GNN applications, including node classification, recommendation system, and knowledge graph. According to the experimental results, we can observe that on Intel CPU, first, The execution time is also affected by the graph neural network architecture. Second, all GN stages have the possibility to become the bottleneck in a GN application. Finally, the aggregate consumes a larger portion of the total execution time. Meanwhile, we also analyze the computing pattern of GN processing models on NVIDIA 100 GPU. According to the experimental results, we can observe that first, the aggregate stage consumes a larger portion of the total execution time. The reason is due to graph data irregular, making it hard to support GN computation efficiently on GPU. To investigate the reasons for the inefficiencies of the aggregate stage, we analyze the pattern of the CPU processing system executing GN models. The results reveal that the aggregate stage has the lowest instruction per cycle due to the much higher cache miss rate and memory bandwidth requirements, which are mostly incurred by the intensive irregular memory access. According to the I/O to computing ratio metric, we also confirm that the aggregate stage involves intensive memory access per operation. More important, CPU and GPU fail to take advantage of massive parallel processing engines on GN model due to the irregular memory access. Nevertheless, neither neural network accelerator nor graph accelerator can process GN models with neural network operation and graph operation, which poses more pressure to the on-chip data buffer and memory access optimization. We take JSON as an example to evaluate how the graph features affect the execution time of GN model. The results reveal that the GN execution time increases with both larger input feature dimension and output feature dimension, while the execution time is more sensitive to the input feature dimension. Meanwhile, we also analyze the power law distribution of dataset used in GNN fields. The results reveal that this dataset also follows the power law distribution, and the accessing frequency to different vertices may vary in a larger scale. In order to design the hardware accelerator for GN model, we first investigate the state of the art JSON accelerator HyGCN, which takes the hybrid computing pattern of JSON into consideration and have two-stage split modules to support neural network computing and graph aggregate. In contrast to the two-stage graph neural network accelerator, we design a graph neural network accelerator with a unified hardware architecture array. The accelerator leverages 1 PE-array to support the feature extraction, aggregate, and update stage. At the same time, the systolic array performs the feature extraction and update stage. Meanwhile, each PE in the same column of the ring edge reduce array is connected to its neighbors in a ring network to perform aggregate operation. Unlike the two-stage structure, our structure can reduce data movement overhead. Each PE is attached by an XPE to perform activation functions, bias operation, and rounding operation in the GN processing stage. And the degree-aware vertex cache is used to cache vertex value to improve data reuse. The feature extraction stage maps the high dimension property of vertex to the low dimension by using the weight matrix, and this stage is simply matrix multiplication operation. In order to support the arbitrary dimension property of GN algorithm, we propose the graph property-aware data flow to decouple the input property of the vertex and the hardware computing structure. The aggregate stage needs to aggregate the information according to the edge information. In order to reduce data movement, we propose the ring edge reduce aggregate data flow to conduct aggregate stage inside the PE-array. In this manner, a PE can select the target vertices to aggregate according to the edge information during the data flow across the ring. The RER data flow makes the hardware design simple yet efficient when the graph is dense, and the vertex properties that flow through the ring are mostly used for aggregation. However, many of the larger graphs are sparse, and the aggregation in PEs is inactive in many cases. To improve the efficiency of the aggregation, we propose to reorganize the edges in each edge bank. To ensure the vertex properties flow through the ring is used as much as possible. With the edge reorganization, we can improve the efficiency of the aggregation and the computation unit utilization. Meanwhile, the result bank are used to store the temporary aggregate results. PEs frequently access the long latency result bank will result in performance degradation. Thereby, we insert a degree of real vertex cache between the result banks and the register file of each PE to cache high-degree vertex for improving data utilization ratio. When the aggregate is summed, the processing order of gene stages, the feature extraction, aggregate, and update stages will not affect the results, but it can change the total number of operations in a GNN. For aggregate, the order of GNN computing leads to different number of operations. When FAU is used, the number of operations is E multiplied by H. When AFU is chosen, the number of operations become E multiplied by F. We also give a computation cost of the first layer of GCN model. In this case, we should select an optimal computation order according to the value of F and H. Thereby, we propose a dimension-aware stage reordering methods based on input and output properties dimension to optimize the computation cost of the graph neural networks. To support larger graph, EnGN turns the larger graph into intervals and shells using a grid partition method. We leverage S# to reuse shared data. Meanwhile, the different tile scheduling can impact the external memory accesses. Thereby, we analyze the I/O cost and propose an adaptive scheduling to minimize the external memory accesses. We build a cycle-accurate simulator to measure the performance of EnGN Accelerator and compare the performance and energy efficiency of EnGN with that of three different baseline architectures: CPU, GPU, and a state-of-the-art GCN accelerator called HyGCN. We evaluate the performance of typical GNN models, including GCN, graph CGPO, gated GCN, GRN, and RGCN on semi-real-world graph dataset and for-static graph dataset using deep graph library and PyTorch geometric software. We compare the performance of EnGN to the baseline computing platforms. The result reveals that EnGN outperforms CPU and GPU in all cases, and the average performance speedup of EnGN on all models over CPU DGL and CPU PYG are 1802.9 and 5108.4. EnGN gains about 48 and 3 performance speedup over the GPU DGL, GPU PYG, and HyGCN respectively on the small dataset. On the larger dataset, EnGN achieves about 19 and 2.61 speedup on average compared to GPU DGL and HyGCN respectively. We evaluate and compare the throughput of EnGN, CPU, GPU, and HyGCN on the GN benchmark. The result reveals that the average throughput of EnGN is about 3,000 giga operations per second, which achieves 53.15% of the peak throughput. The computing efficiency of EnGN typically keeps steady and does not vary much with the model and the dataset, while CPU and GPU are more sensitive. The energy efficiency of EnGN is 6.2 higher than HyGCN on average and outperforms CPU and GPU. we compare the performance of GNS on EnGN with edge reorganization and EnGN without edge reorganization. The edge reorganization improves the performance of EnGN, and it can work much better for larger dataset. Meanwhile, we also compare the performance of DSR and graph tunneling. The result reveals that the DSR and the proposed graph tunneling are beneficial to the GNN processing performance on both CPU and GPU solution, and EnGN outperforms all the implementations on CPU and GPU with and without such improvement. In summary, in order to customize the hardware accelerator for graph neural network, we first generalize the architecture of a typical GNN algorithm and construct the GNN processing model, which contains 3 key stages. After that, we perform a workload analysis for 3 key stages to guide the hardware design. Then, we present a high-throughput and energy-efficient accelerator EnGN specialized for large graph neural networks processing. EnGN adopts a unified hardware architecture to perform the key stages of GNN and edge-reduce update data flow with edge reorganization methods to support aggregation stage on GNS, graph tunneling, and scheduling technique, cooperating with the well-designed 3-level memory hierarchy to process a large graph efficiently. Finally, EnGN outperforms CPU and GPU platform in GNN model inference and energy efficiency, and it also achieves 2.97 speedup and improves energy efficiency by 6.2 on average compared to the state-of-the-art GCN accelerator HyGCN. Thank you for your attention.